Picture this. You deploy a state-of-the-art React agent using GPT-4 to handle customer refunds. It works perfectly in your local Jupyter notebook. But 2 a.m. on a Tuesday, a strange edge case hits. The agent encounters a malformed JSON response from a legacy database API. Instead of failing gracefully, the LLM reasons that it should try again. It enters a recursive loop, calling itself 600 times in under 3 minutes. By the time your monitoring alert triggers, you've burned $500 in API credits and your rate limits are exhausted, bringing down every other service dependent on that model. This is the token burn catastrophe. Without a strict execution harness, an agent is essentially a script with an infinite loop potential where the break condition is governed by probability rather than logic. In production, mostly works is the same as broken, and the financial risk of unmanaged agency is a debt no architect should sign off on. But this financial disaster is just the tip of the iceberg. Wait until you see how these agents lose their cognitive consistency entirely when the state isn't anchored by code. This lecture will reveal exactly how to prevent this rogue behavior by 2026. The real danger isn't just the cost. It's the black box of non-deterministic decision-making. When you build an agentic system where the LLM decides the control flow, you are essentially outsourcing your business logic to a stochastic engine. On Monday, the agent uses tool A, then tool B. On Tuesday, after a minor backend update or a slight shift in model weights, it decides tool B, then tool C is better. This probabilistic drift makes debugging nearly impossible. You can't write a unit test for a thought process that changes every time you hit run. Senior architects are finding that vibes-based engineering fails the 5 nines availability test required for enterprise software. We are currently stuck in a paradigm where we treat the LLM as the brain and the controller, but as any seasoned engineer knows, a brain without a skeletal system and a nervous system the harness is just a floating, unreliable mass. If we can't predict the path, we can't trust the outcome, so how do we move from this probabilistic chaos to the governed execution plan for 2026? Let's look at the roadmap to deterministic agency. By 2026, the industry is moving away from the agent as a prompt era toward the harness architecture era. In 2023, we focused on prompt engineering and simple RAG, hoping the LLM would figure it out. By 2024, we saw the rise of basic frameworks like LangGraph or CrewAI, which introduced rudimentary state machines. However, the 2026 roadmap demands deterministic agency. This means the code harness the hard-coded Python or Rust wrapper is the master, and the LLM is merely a modular reasoning engine called it specific, predefined junction points. We are shifting from LLM-centric designs to code-centric orchestration. In this new paradigm, the harness enforces schemas, manages memory persistence, and handles retry budgets before the LLM even knows an error occurred. The evolution is clear. We are taking the steering wheel back from the probabilistic model and putting it into the hands of the system architect. The shift is happening now, but what does this governance actually look like when implemented in a live, high-traffic production system? We need to define the layers of this architectural safety net. The promise of the harness architecture is simple: architectural safety. It's about moving from probabilistic chaos where you pray the agent follows instructions to governed execution, where the code physically prevents the agent from violating business rules. This involves 3 pillars: schema enforcement, state persistence, and resource budgeting. When you wrap an agent in a proper harness, you gain the ability to scale predictably. You can finally tell your stakeholders, this agent will never cost more than $2 per request and will always output a valid JSON. This transition is not just a trend, it's a requirement for the industrialization of AI. We've seen the nightmare of unharnessed agents running rogue and burning budgets, but now we have the blueprint for the cure. In the next chapter, we will dismantle the LLM as the brain myth and introduce the true master of the house, the code harness architecture that will define the next decade of AI development. Are you ready to see the code that actually controls the beast? In the early days of LLM implementation, we focused on the model-centric approach where the LLM was expected to generate code and execute autonomously. This led to a production nightmare of non-deterministic outputs and security risks. As an architect, I've seen systems collapse because the LLM chose a slightly different library version or a deprecated API. In the 2026 paradigm, we flip the script. We are moving toward a code-centric harness. Here, the code is the master framework, the chassis, and the LLM is just the engine. The code defines the schema, the types, and the allowed transitions, while the LLM provides the probabilistic reasoning within those rigid boundaries. This shift ensures that the system's reasoning does not override its reliability. It is the difference between a hallucinating script and a production-grade agentic system. Let's define what the recent 102-page survey calls a code harness. It isn't just a simple wrapper or an API caller. It is a dedicated governance layer that enforces system boundaries. This harness includes symbolic parsers, runtime monitors, and execution sandboxes. In senior-level architecture, we treat the harness as the ground truth. When an LM produces a thought or an action, the harness intercepts it, validates it against the pedantic schemas or type definitions, and only then allows execution. This turns a standard LLM into a guided agent. Without this governance layer, you aren't building a system, you're just hoping the model behaves today the same way it did yesterday, which is a recipe for failure in enterprise environments. We must treat the harness as the primary citizen of the codebase. How do we actually constrain the infinite possibilities of an LLM? We do it through state management and structural constraints. Imagine a state machine where the LLM is only allowed to propose transitions. If the current state is processing payment, and the LLM suggests jumping straight to shipping item without a payment confirmed signal from the harness, the code simply rejects the transition. This creates a safety net where the LLM cannot physically or logically bypass the business rules. In 2026, we use tools like advanced finite state machines, FSM, integrated with semantic parsers to ensure every LLM action is a valid state transition. This approach effectively solves the state explosion problem in complex agents, where the model gets lost in its own reasoning history. By keeping the state in the code, the model stays on track. To build a robust harness, you need to understand its layered anatomy. At the very bottom, we have the hard runtime. This is the execution sandbox, often using micro VMs like Firecracker or secure containers to prevent the agent from accessing the host system. Above that sits the semantic middleware. This is the translation layer that uses instructor-led parsing or Pydantic to turn messy LLM text into clean, typed objects. Finally, we have the logic gatekeeper or the orchestrator. This is where your business logic and control flows are codified. In production, a common mistake is blending these layers together. If your orchestrator is just a giant string of prompts, you've failed as an architect. Each layer must be decoupled so that you can swap your LLM engine without breaking the chassis logic. This modularity is the secret to scaling AI agents. Finally, let's map the flow of control and data. In a well-architected system, control flow is strictly held by the code. The harness decides when to call the LLM, what context to provide, and what to do with the result. Data flow moves from the user, through the harness for sanitization, into the LLM for semantic processing, and then back through the harness for verification. This ensures semantic integrity. If the data flow bypasses the harness, you create shadow logic that is invisible to your monitoring tools. In my experience, the most successful agents in 2026 use this bidirectional verification. The harness doesn't just watch the LLM, it actively steers it by injecting constraints into the context window based on the current state. This closed-loop system is what makes the master-engine relationship work in practice. Now that we understand the anatomy, how do we actually build the pillars that support it? You have likely seen LLMs enter infinite loops or get stuck in logic traps during complex tasks. Relying on an LLM to figure out the flow of a multi-step business process is a recipe for disaster in production. This is why our first pillar is orchestration. In a high-stakes environment, we don't let the LLM wander aimlessly. Instead, we use code-specifically directed acyclic graphs or state machines to define the boundaries of the agent's movement. Think of the LLM as the engine, while the code harness acts as the transmission and steering wheel. Without this hard-coded structure, your agent will eventually hallucinate a path that doesn't exist, leading to unpredictable API calls and state corruption. By 2026 standards, the state-of-the-art involves state-first design where the LLM suggests the next transition, but the code harness strictly enforces the validity of that transition before execution. This separation of powers ensures reasoning stays flexible while execution remains deterministic. But reasoning logic is only half the battle. How do we stop an agent from accidentally deleting your production database? Giving an LLM raw API access is like giving a toddler a chainsaw. It is not a matter of if it fails, but when. The second pillar is tool use, specifically focusing on sandboxing and safety. In the field, we see teams struggle because they expose internal functions directly to the agent's prompt. The professional approach is to implement an execution sandbox using technologies like YSM gvisor or isolated Docker containers. This harness intercepts every tool call. It doesn't just pass strings, it validates schemas, checks permissions, and rate limits requests. If the agent tries to run a drop table command or an unauthorized sudo, the harness catches it before it hits the infrastructure. This layer also provides a dry run capability where the agent can see what happened without actually making changes. This level of safety is what separates a toy chatbot from an enterprise-grade agentic system. Standardizing these tools into a predictable protocol is what makes the difference between a prototype and a product. To make tool use reliable, we need a tool protocol. This isn't just about describing the function. It's about defining the contract between the code and the model. Look at this interface implementation. We use decorators or specific structures to wrap every tool. This wrapper automatically generates the JSON schema that the LLM sees, while also handling the error parsing when the tool fails. When a tool returns an error, the harness doesn't just crash. It formats the error in a way the LLM can understand and learn from. For example, if an API returns a 403 forbidden, the harness can provide a hint like "you lack permission X, try searching for an alternative." This structured feedback loop is critical. Without a strict protocol, the LLM will constantly hallucinate arguments or fail to handle edge cases in the data it receives. Even with perfect tool calls, an agent is effectively demented if it forgets what it did 2 steps ago, which brings us to memory. The third pillar is memory, and I'm not just talking about a long string of chat history. In complex agentic systems, we need a hierarchical memory structure. At the top, we have ephemeral memory, the immediate context window of the LLM. Below that is short-term memory, often implemented as a Redis cache or a local key value store to track variables and current session states. Finally, there's long-term memory, utilizing vector databases for RAG and persistent storage for agent identity and past successes. The code harness is responsible for context management, deciding what to keep and what to truncate. If you let the memory grow unchecked, the LLM's reasoning quality degrades as it hits context limits. A sophisticated harness performs memory summarization or semantic pruning to ensure only the most relevant memories are injected into the prompt at any given time. Memory gives an agent identity, but even a genius with perfect memory can hallucinate unless we force it to look in the mirror. The final and perhaps most crucial pillar is the reflection loop. This is the harness forcing the LLM to verify its own logic before any real action is taken. We implement this by creating a critique-correct cycle. When the primary agent generates a solution, the harness doesn't execute it immediately. Instead, it triggers a reflection step, sometimes using a different, more specialized model or a strict rule-based validator to ask, does this output meet the safety and logic constraints? This process effectively catches hallucinations and lazy reasoning. If the reflection finds an error, it sends the feedback back to the agent for a second pass. In production, we've found that this single addition can increase task success rates by over 40% in multi-step coding or data analysis tasks. It turns the agent from an impulsive talker into a reflective worker. So we have the logic, the tools, the memory, and the reflection now. Let's see how they all snap together into a single, bulletproof architecture. To summarize, the 4 pillars: orchestration, tool use, memory, and reflection form the foundation of what we call the agentic architecture. When these 4 elements are managed by a robust code harness, the LLM stops being an unpredictable black box and starts behaving like a reliable system component. Orchestration provides the map, tool use provides the hands, memory provides the history, and reflection provides the eyes. Without this framework, you're just prompt engineering your way toward a brittle system that will break at the first edge case. In the coming years, the mastery of this architecture will be what defines a world-class AI system architect. The theory is solid, but the devil is in the implementation details, especially when we start writing the actual Python harness in the next chapter. We will move from these abstract concepts to a hands-on implementation walkthrough using real Python patterns. In the industry, I often see developers start with simple linear chains and quickly hit a wall. Real-world agent tasks are rarely linear. They require loops, branching, and backtracking. This is where a graph-based state machine becomes your primary harness. By using libraries like LangGraph, you define the agent's logic as a set of nodes and edges where the state is explicitly managed. Each node represents a discrete step, like calling an LLM or executing a Python tool, and the edges determine the flow based on the current state. If you don't define these cycles explicitly in your code, the LLM will just wander off and lose context. Think of the harness as the railway tracks and the LLM as the locomotive. Without these tracks, even the most powerful engine ends up in a ditch during complex, multi-step reasoning. But defining the path is only half the battle. The data moving across these tracks must be bulletproof. So how do we stop the LLM from sending us garbage data that crashes the entire system? Senior developers know one painful truth. LLMs are notorious for hallucinating JSON structures. They might skip a required field or wrap the response in markdown blocks that your parser can't handle. This is where Pydantic acts as your enforcement officer. By defining a strict schema for the agent's output, you create a validation layer that catches errors before they reach your core business logic. Using tools like Pydantic's base model allows the harness to coerce the LLM into returning exactly what we need. If the LLM returns an invalid type, the harness immediately flags it. In a production environment, you cannot afford to have a known type error deep in your stack just because a model decided to be creative with its output format. We use these schemas to define the API contract between the unpredictable model and our predictable software. But what happens when the validation fails? Do we just let the agent crash? Actually, the harness should be smarter than that. In the world of agents, exception handling isn't just about logging errors. It's about building self-correction loops. When an LM fails a validation check or a tool execution times out, a primitive harness would simply crash. A professional-grade harness, however, catches these exceptions and feeds them back into the LLM as a reflection prompt. We tell the agent, hey, you provided invalid JSON. Here is the error, please try again. This retree logic, embedded directly into the state machine, transforms a fatal error into a temporary delay. You should implement specific catch blocks for common LLM failures like rate limit errors or context window exceeded. By wrapping your model calls in these robust retree patterns, you increase the reliability of your agents from 70% to nearly 99%. However, if you're retrying multiple times, you might be burning through your budget without realizing it. This leads us to a critical operational challenge. How do we actually observe and control what these agents are doing behind the scenes? Once your agent is running in a harness, it becomes a black box unless you implement deep tracing. You can't just look at the final output. You need to see the entire reasoning, trace the intermediate steps, the tool calls, and the raw prompts that led to the result. In modern stacks, we integrate tools like Langsmith or OpenTelemetry directly into the harness. This telemetry data allows us to audit why an agent took a wrong turn at step 4 of a 10-step process. In the field, I've seen teams spend days debugging an agent only to realize the prompt was being truncated in the middle of a loop. Tracing gives you the X-ray vision needed to fix these invisible bugs. Without a centralized way to view these traces, you're essentially flying blind in a very expensive storm. Speaking of expense, monitoring the cost of these traces is our next high-stakes hurdle. Agents can be dangerously expensive if they enter an infinite loop or call a high-cost model like GPT-4o unnecessarily. A robust harness must include circuit breakers, hard limits on token usage, execution time, and the number of steps in a single graph run. In production, I always set up threshold monitors within the code itself. If an agent exceeds 10 iterations or consumes more than 5,000 tokens for a single task, the harness should auto-terminate the process and alert an engineer. We also track latency per node. If a specific tool execution is consistently taking over 10 seconds, it's a bottleneck that the harness needs to report. You should treat agent costs like a cloud bill. If you don't monitor it in real time, you'll get a very unpleasant surprise at the end of the month. But keeping costs down is only part of the puzzle. You also need to ensure that every update you push actually improves the agent's performance. Finally, we need to talk about deployment. In a traditional app, you version your code. In an agentic system, you have to version your code, harness, your system prompts, and the underlying model. This triple versioning makes CI/CD for agents uniquely difficult. Before any deployment, your harness should run through a suite of evaluations, automated tests that check if the agent still reaches the correct conclusion after a code change. If you change the harness logic to handle retries better but accidentally break the tool calling schema, your evils should catch that instantly. Use a checklist approach. Ensure environment variables are isolated, model versions are pinned, never use latest and evaluation datasets are updated. This rigor is what separates a weekend project from a production-ready AI system. Now that we have the harness and the monitoring in place, it's time to look at the scars. In the next chapter, I'll share some real war stories from the field where things went spectacularly wrong despite these best practices. In a production environment, when autonomous agent makes a mistake that costs thousands of dollars or deletes critical user data, saying the model hallucinated will not satisfy the legal or compliance teams. As senior architects, we must implement what I call the box recorder for agents. Every single action proposed by the LLM and executed by the harness must be cryptographically signed. We use JSON Web Signatures (JWS) to ensure that the audit trail is immutable. This means that if an agent triggers a delete user tool, the harness logs the prompt hash, the model version, the exact timestamp, and the authorization token used. By the time 26 rolls around, these signed logs will be the industry standard for AI accountability. You need to be able to prove exactly why the harness allowed a specific call to pass through its validation layers. Without this, you aren't running an enterprise system, you're running a high-risk experiment. But even if we have the logs to prove what happened, how do we stop the fire from spreading across the entire microservice mesh when an agent goes rogue? This brings us to the concept of active fault isolation. Let's talk about the blast radius. I've seen cases where a looping agent bombarded a downstream legacy API with 10,000 requests in seconds because the model got confused by an error message. In a standard microservice architecture, we use circuit breakers like Resilience4j or Istio's filters, and agent harnesses are no different. You must wrap your tool calling logic in a circuit breaker that monitors the error rate and latency. If the agent starts failing or hitting rate limits, the harness should trip the breaker, cutting off the agent's ability to call that tool until the system stabilizes. We also use the bulkhead pattern to ensure that an agent dedicated to customer support cannot consume all the database connections needed by the checkout agent. By isolating the harness execution environment, ideally in a sandboxed container, we ensure that even a total agent failure doesn't take down the entire platform. It's about containing the chaos within a defined boundary. Now, building these safety cages is great, but what if the architect themselves hands the agent the keys to the kingdom by mistake? Let's look at the anti-patterns that end careers. The most dangerous anti-pattern I see today is excessive autonomy. Some developers think it's brilliant to give an agent access to a raw bash shell or the OSDA system, command in Python. This is essentially handing a loaded gun to a toddler who might be influenced by a malicious stranger. Prompt injection is a real threat. If an attacker can trick your agent into running RF via a tool call, your agentic dream becomes a nightmare. Never give an agent more privileges than a standard, restricted service account. If it needs to manipulate files, use a dedicated, scoped library that only allows operations within a specific subdirectory. We call this least privilege agent design. Another trap is prompt leakage, where the agent reveals its internal system instructions to the user. Your harness must act as a content filter on the way out, scrubbing any sensitive internal logic or API keys that the model might accidentally spout. These mistakes are easy to make, but incredibly hard to fix once a breach occurs. Is the solution then to wrap the agent in 1,000 layers of complex boilerplate? Actually, that brings a different kind of pain. Finally, we have the over-engineering trap, which often manifests as latency bloat. If your harness has 20 different middleware layers for validation, logging, and pre-processing, you might add 1 or 2 seconds of overhead before the LLM even begins its first token generation. In a 2026 landscape where users expect real-time interaction, this is unacceptable. You have to find the Goldilocks zone: enough harness to be safe, but lean enough to be performant. Don't build a god harness that tries to handle all the business logic. Let the business logic live in the tools, and let the harness focus on the peer-to-peer execution bridge peer-to-peer. Another common mistake is ignoring the cost of retries. If an agent fails and your harness automatically retrieves 3 times with a GPT-4 class model, your bills will skyrocket without any improved outcome. Smart harnesses use exponential backoff and model grading to decide if a retry is even worth it. Balance is the key to a sustainable agentic architecture. Now that we've seen the scars and learned from the failures of the early adopters, let's look at the final horizon, the 2026 blueprint for the next generation of AI systems. We've covered a lot of ground today, but if you take away only one thing, let it be this. In the agentic era, code is no longer just a consumer of AI, it is the essential harness that makes AI useful. We are moving away from the prompt and pray approach that dominated the early 2020s toward a deterministic, architecturally sound framework. This means implementing rigorous input validation, structured output parsing with pedantic, and state management that survives LLM hallucinations. By 2026, the industry will look back at raw LLM calls as we now look at manual memory management as something too risky and inefficient for production systems. The code harness is your insurance policy for reliability, ensuring that even when the model fails, the system stays within its guardrails. But how do we align this technical structure with the evolving role of humans in the loop? Let's look at the 2026 organizational blueprint. Looking toward 2026, the landscape of software development is undergoing a fundamental shift where the agentic architecture becomes the standard. In this ecosystem, the LLM acts as the reasoning engine, a powerful but volatile worker, while the code harness serves as the skeletal structure providing direction and safety. Humans are no longer just writing individual functions. We are designing the constraints, the feedback loops, and the success metrics for these autonomous systems. This isn't just about automation. It's about human-in-the-loop orchestration, where the architect oversees a fleet of agents within a strictly defined sandbox. We are moving from being coders to being system choreographers. This high-level vision is great, but what does your Monday morning look like? We need to translate this into immediate action to get your current projects ready for this future. To transition from scripts to a harness, start by refactoring your most volatile LLM calls into a dedicated harness layer. The first step is implementing a strict tool registry. Never let an agent call a function without a schema-validated interface. Next, move your execution into a sandbox. If an agent generates Python code, it must run in a containerized environment, not on your host machine. Finally, implement a state manager that persists the conversation history and environment variables independently of the LLM's context window. These 3 steps transform a fragile demo into a resilient foundation. You don't need to rewrite your entire stack overnight, but you must start treating AI interactions as untrusted external inputs that require a rigorous wrapper. Refactoring code is just the beginning. The real challenge is maintaining a rigorous mindset as the technology shifts under our feet. As we wrap up this lecture, remember that AI engineering is evolving into a rigorous software discipline, not a series of clever hacks. As a senior developer or architect, your value lies in the harness you build around the model. Treat LLM outputs with the same skepticism you would treat a third-party AP. Validate everything, log everything, and always have a fallback. The agentic paradigm isn't about giving up control. It's about exercising control through more sophisticated architectural patterns. Keep studying the latest survey papers, stay active in technical communities, and never stop experimenting with new ways to constrain and direct these models. This concludes our journey through the code harness paradigm. Apply these principles, and you'll be building the robust, production-grade systems of 2026 today. Stay tuned for our future deep dives into multi-agent orchestration and security.